Okay, welcome to the Bucky Weekend call for February 15, 16, depending on what continent you're on, 2025. It's 40 minutes in. We've had a great discussion about Bucky's ideas about automation and automating education. That another group, Richard's in, was doing that. And we started talking a little bit about automated education and then talked a little bit about the political issues going on right now around with Trump and the Doge with Elon Musk and talked about how we legitimize, are we going to have a universal income like Bucky talked about in the first place? And if we had that right now, all the people that are upset would be totally quiet and happy because they just get their monthly income. So we'll see if that happens in the next while. Anyway, we've had a great discussion. I shared a little bit about um, working on my dimensionality through 60 degrees that Richard and I have been working on, or when no one's here and it's just me and Richard, we just spend time and talk about the 60-degree to 90-degree paradigm and how do we create dimensionality and look at things from the tetrahedron. Did you guys see that I sent out a clip from the podcast, from the All In podcast that talked about the tetrahedron of conversations? It's very cool.
Yeah.
Because one of the guys is talking there. He says, well, first, 2 is a conversation, 3 is kind of exciting, 4 is about the limit. When you get 6 people at the table, you split into small groups. 4 is about as best as you can handle. I thought, man, here's a perfect explanation of the tetrahedron in relationships, right? It really works. And so I sent that out thinking that was quite fun. Okay, and Anne is not here. She has company in from China, and she's entertaining them today I think as the Chinese New Year winds down, and she'll be joining us next week, most likely. With all of that in mind, we're going to do some reading here, starting at chapter 98. I'm sorry, page 98 in the fuller explanation. We're going to be reading about spatial considerations. And here we go. Richard, how are you feeling, and what do you anticipate tonight?
Well, I'm feeling pretty good coming off of the trim tab discussion this morning and getting into some of the theme and the message that Fuller was communicating about education automation back in the 1960s as he spoke to the presidents and other academics at University of Illinois Carbondale campus. So to be able to come out of that kind of discussion and go into further dialogue related to Amy Edmondson's fuller explanation is really a nice capstone on the Saturday afternoons or the Saturday morning session into the Saturday evening session. So looking forward to it. Joe, how are you feeling and what are you looking at for expectations?
I'm feeling actually pretty good. It's been a hectic 48 hours, but it's been things are well. It's as far as my expectation is to kind of really start to take what what we're reading with fuller explanation and really map it into cosmography. So I really think that that's actually seeing the relationship between those 2 books has actually been really beneficial for me. I think that they have kind of different approaches, obviously, with how they're approaching the topics themselves, but seeing the relationships between those 2 books has actually been interesting, helpful for me as well. For cosmometry, I said cosmography. But nonetheless, I think that there's Lefret's book and Amy's actually has been a really nice combination, and just seeing the combination between those two is actually what I'm hoping to continue to get out of these sessions. Steve, how do you feel? What are you looking to get out of today's session?
Well, I'm with you. I think that working on the cosmometry book together with this book, Fuller Explanation, and how the two work together is really profound. And it adds a lot. And I'm looking forward to tonight's reading. We've started here with vector equilibrium, which is the main topic in cosmometry, and that happens to be chapter 7 in Fuller Explanation. So we're looking at vector equilibrium, and then we talk about last week, or the last few pages, 96 and 97, we did, and part of 98, most of 98, we talk about entropy and how it relates to vector equilibrium. And tonight we're going to go with spatial considerations. We're going to start talking about packing. So I too am looking forward to putting all this together and delighted to participate. Without further, let's go for it here. I'm going to find the book. Here it is. And then I like when we trade off reading. So I'm going to start reading for a little bit and we'll pass it along. So at the bottom, page 98, here we go. Spatial considerations. A symmetrical distribution of energy events involves a large number of equivalent separation distances. I'm just going to pause. Energy events. This whole concept is very cool. It's helping me understand perturbations in the electromagnetic field, the very concept of happenings instead of, at the beginning of this book, one of the things that is stressed was that nothing is permanent. Everything is coming and going, and that I may look at a steel building in LA, but in 1,000 years' time, or 2,000, maybe that building came and went. In other words, whether a thing is a thing depends on the perspective of time at which we look at it. So this idea of the symmetrical distribution of energy events involves a large number of equivalent separation distances is hugely profound. So thank you for letting me editorialize. For a more tangible, what's that?
Let me just speak to that too, because what it just came across to me as if energy events, like events, are equivalent to the corners or the nodes of the tetrahedron,
right,
and they involve a large number of equivalent separation distances, that, to me, that also could be substituted with the word vector,
yes,
an equivalent vector distance. And so now what you have is events or corners and vectors surfacing out of that statement.
right,
Which is another way too, for me now, is saying the principles of compression and tension in tensegrity are also in that sentence, because you've got energy events in my mind as compression items, and the equivalent separation distances are tension items.
cool, wonderful.
Anyway, that's what popped in my head.
Very cool. Joe, anything coming up for you there on the first sentence of this paragraph? Or shall we continue to read?
No, I mean, I think actually that was actually what Richard just shared was actually a good summation of it, and looking at it as a connection between the nodes and as events.
Right on.
And I'm, and that's where I start to think about literally like about the relationship between the nodes, but things like graph theory. So that's what initially had come up for me.
Cool. I'm going to add one more editorial comment, because as I've been looking at these perturbations or energy events in the electron field, I've been looking at tornadoes in the environment of Earth. And while there's this huge amount of energy rotating around the eye of the hurricane, in the hurricane itself, there's very little movement going on, as though it were a 0-point vector. And all the energy is around that event. and the way that that energy relates to the things around the hurricane, causing all the chaos. It's the equivalent separate distances and the energy between those distances, between the 0 point vectors, that make reality the way that we see it. And at least that's one aspect of what I'm seeing there.
Yeah, I mean, yeah, and also just spotting the patterns between these things are actually something that's also very important to kind of recognize between these events and noticing essentially yeah, I mean, essentially noticing the changes based off of the certain certain relationships between the nodes.
Right.
So anyway,
the next sentence refers back to the entropy conversation. Oh, crud. My gosh, it went back way faster than I thought. Let's see what was going to happen here.
Oh, I see. Wow.
I'm at page 98, and I'm all of a sudden I'm back to 85 just because I grabbed that stupid elevator. Because what I want to do, here we go, vector equilibrium. Then we talk about, there we go. At the top of page 98, it talks about entropy. And so here we go. For a more tangible image than provided by gas molecules in the entropy examples above, picture a large room full of people asked to spread themselves out for stretching exercises. If the room is sufficiently crowded, a more or less triangular pattern in the distribution of people can be observed as a result of individuals trying to maximize the area of their territory. Each person feels he or she has more space when the distance between people are maximized, which is the case when all distances are close to equivalent as possible. If it's hard to see why that's equivalent applies in a triangular pattern, read on. Close packed cookies. Triangular versus square pattern. Triangular pattern enables one more row of cookies than square patterns with the same minimum separation between the cookies. So if you count these rows, there are 7 rows here and there are 6 rows here. Oh, geez. Holy freaking mackerel. What just... Suddenly I'm back at the table of contents. Oh my gosh, this is wonderful.
That's a great image.
it is a great image.
And I don't think I actually really saw it that way until we were looking at it today.
That's a really interesting way of actually discussing packing or leading it up to discussing packing, spherical packing.
Wow. And I've got, geez, I'm at page 112. Hang on a second. I got me a new mouse, which should give me a little bit more control. Whoop, I know we've been there before. There we go. There we go. Okay, dynamite. Wow. And as soon as I hit that down arrow, it zoomed back up there again. That is so strange. I'm not going to hit the down arrow. I think we looked at that table before. Yeah. Yeah. Angular topology. Here we are. The vector. Now let's see if I can control this puppy. 96, 97. Okay, 98. And now I've touched inside it. Good, we got it. Think about baking cookies in a tray. Intuition, rather than geometrically training, intuition, rather than geometrical training, tells you that the cookies in successive rows should be offset to maximize the number which can fit on a tray without spreading it into each other. Observe figure 7.3 above. that a square distribution with the same minimum separation between cookies wastes considerable tray area, resulting in fewer cookies than in a triangular pattern. In the same way, people in a room naturally quite unconscious of the advantages of triangular distribution, milling around until each carves out a desirable comfort zone can end up by increasing the overall symmetry. This organization does not require a director at the head of the room. Nature behaves in the same manner, seeking the most comfortable resting position. Forces continue to push or pull until counterbalanced, and in the absence of other influences, symmetrical considerations dominate. This is Fuller's words, an a priori absolute mystery of why nature behaves this way, which is beyond explanation. The question is thus how universe operates. Okay. And I'm ready to relinquish somebody else who wants to read.
Yeah, I can read.
Okay, let's rotate around those two.
The advantages balances suggested by the term equilibrium can be expressed in terms of symmetry. The properties of space are necessarily behind all events and reactions in nature. Hence, Fuller's assertion that forces in both the macrocosmic and the microcosmic structures interact in the same way. Space is the same on every scale, embracing and molding the most economic equilibrious packings. With the conceptual foundation in place, we can now describe the model proposed by Fuller to represent equilibrium. In his words, we seek the simplest omni-accommodative system able to model the behavior of complex systems. Basically, we want to draw a better yet build that much discussed balance of forces. To accomplish the desired result, a model must incorporate two aspects of Fuller's geometry. First, it must consist of vectors, and secondly, it must cover all directions. In short, we want to illustrate an equilibrium of vectors in space.
Cool. Did you guys see the video I sent out, a little short on vectors in space? It's really cool. Maybe we'll have time to see it tonight if it continues to be relevant.
Yeah.
For some reason, oh my gosh. Okay, here we go. All right, good.
So planar equilibrium, spatial configurations tend to be difficult to visualize, whereas fiat patterns are not. So we start with the page. Draw a vector of some arbitrary length, which we designate unit length, in any direction. To counteract that force, we position a second vector directly opposite the first, head to head. They have the same magnitude and opposite direction and are therefore balanced. It is an unstable balance, however. It's an unstable balance, however, easily knocked out of the equilibrium by a force from any other direction. Suppose that the original two forces push on a body with equal strength from the east and west. A force from the north or south, even if smaller than the east-west pair, can easily destroy that unstable equilibrium. So how can we most efficiently ensure the stability of the body in question?
Okay, let's just take a second here. I want to go look at that figure. It's on the next page. And hopefully it won't send me off into oblivion. There's your figure A. That's what she's talking about. She's talking about these two vectors that are hitting force to force.
Right.
And then she's saying, now what other alternatives are viable? Any other comments or questions before we go back to the reading?
No, I'm just drawing something out real quick.
Okay, so here's where, to counteract the force, we position a second vector directly opposite the first vector, head to head, like in figure 4a. We just saw that. And it's going from east to west. And she's saying a force from north to south, even if smaller than the east or west pair, can easily destroy the unstable equilibrium. So how can we most effectively ensure the stability of the body in question? Go ahead if you want to
We'll
continue.
find that. Yeah, we'll find that in a minute. Suppose instead that the forces are directed
Jeez. There we go.
outwardly from the body. Fuller's explosive potential, as quoted in the first paragraph of this chapter. To begin with, imagine 4 equal vectors heading north, south, east, and west. That is, in the positive and negative directions of the x and y axes. To counteract the 4 explosive forces, we need equivalent restraining forces, implosive or embracing. Fuller's embracing vectors are not technically part of the conventional language of vectors. Having neither head nor tail, their effect is simply restraining, like a net, and their magnitude is still assumed to be represented by their length. As strength is graphically depicted by vector length, we soon find that there is no easy way to draw 4 embracing vectors of unit length. In figure 7-4b, the ends of our 4 explosive vectors are interconnected by these new lines, and new lines are approximately 1.414, i.e.
Square root of 2.
Is that
The square root of 2.
square? Yeah, square root of 2. Yeah, times as long as the outward forces. The longer vector lines represent more powerful forces and thus overpower the explosive potential, meaning that the whole display must collapse inwardly. Okay, that makes sense. That last.
It doesn't make it much sense to me, but I'm going along with it so
Well,
far.
I'm just saying how the collapse that's the part that made sense to me.
Well, I'm not sure why we went from 2 vectors butting heads to the negative and positive on the XY axis. I'm not sure why we did that, but I'm going along with the story because it sounds really good so far. Anybody else want to comment?
Well, my comment on B is, again, trying to put my head around the vector lengths of 1 and the square root of 2 on the broken line vectors, which to me is another way of saying that's the hypotenuse. It's a little bit longer.
Right.
And that's what happens when you have a 90-degree triangle. What we talked about last week, that
Right.
rectangular. But my eye, when I look at that, tells me that the square root of 2 lines are equal to 1. In other words, I want to see 60-degree angle faces. That's what I see. And so that way I see equal vector lengths.
On inside the square. Because each of these
well,
represent 1. So A
see,
squared plus B squared equals C squared. That's why 1 and 1, you have a square root of 2.
Yeah, no, I understand that. But
Yeah.
now I'm so used to taking a visual like that and turning it into a tetrahedral image.
Gotcha. Yeah.
And so in other words, the X and Y are not intersecting the way in which they're laid out there. One is behind the other, which then I think would turn it into that equal vector between the 4 points. So it's interesting. What happens when you're taught to work with the XYZ 90-degree coordinate system,
Right.
and when you're also taught to use the 60-degree coordinate system?
Right.
Yeah.
No, and most people aren't going to see that B is a tetrahedron because if you take call the horizontal line the x-axis and call the vertical line the y-axis. If you turn this image sideways and you have y over here and you have x over here, you've got a tetrahedron. Most
Yeah.
people, I don't think, would see the tetrahedron in B.
No, because they've got to take that AB line and pull it out,
Exactly.
toward them, and or push the other line back.
Right.
Right.
And then you see that they're not crossing each other.
Right.
But yeah, but because we're taught the other way, it's most people will see the cross.
And I think this is designed as a two-dimensional figure where X and Y are actually crossing.
Yeah, exactly. Yeah.
Yeah. Yeah,
So-
interesting, huh? In fact, you could actually see this as an octahedron if you went into 3D because it's sticking out over there and it's sticking back behind there just as far. This could be an octahedron. But
That's right. You could create a square on that horizontal line.
right.
Oh, yeah,
If I could just go up here and grab this and tilt it like this, and suddenly that horizontal line appeared to be a square, this
Right.
would be an octahedron.
Yeah.
And if I could grab one of these points and twist it sideways then we'd see the tetrahedral aspect of it. It would also be 3D. Very interesting. And still, I'm not exactly sure why she's having us do all this. Why did we go from these two vectors nose to nose? Because she says it's unstable. And so
what I think she's getting at is that when you actually see the connectors, you will see that you'll see the balance stabilizing.
yeah, and she
And so
stabilized it.
that to me is that number A is now interesting for me because that's the classic definition of balance. When you
Yeah,
have the forces from both sides countering each other. But then she goes one step further and says, it's just suspended there and
right,
it's not stable.
right.
You could blow on it and it would disappear. So
Yeah,
balance in that sense is not stable. Yes,
right.
it's balanced, but momentarily,
That's right.
yeah.
Yeah, very cool. So let's continue to read.
Yeah.
Whoop.
We might then choose to add more outward force what was this like forces maintaining symmetry by an additional unit vector in between each of the original four.
Right.
Now we have 8 equal forces emanating from one point, and the resulting 8 embracing lines are only 0.765 times as long as the unit length. Too small to restrain the explosive forces. This imbalance leads to outward dispersal of the hypothetical system.
So this reconfirms that everything she's saying here is 2D. We're
Right.
starting with two vectors here, and then we're instead of the two vectors facing each other, we're having them crisscross each other as in an XY, a 2D XY. And now we're adding in the extra horizontal lines, and thus we've got this hexagonal thingy. Oh, it's octagonal. This is octagonal. We're about to go ahead.
Yeah, no, that's an interesting progression. That's an interesting way of actually, kind of demonstrating that.
Yeah.
Going from the two lines actually going head to head with the east and the west,
Right.
introducing it as lines that are intersecting versus actually lines that are moving in opposition to one another.
And to continue, go ahead.
Yeah.
And to continue the wording, you got east and west here. Now you have east, west, north, and south.
Right. Right.
And now you have north. What do you call it? South by northwest. By
Right,
these are the
northwest,
cardinal
east.
directions, and these are what are these called? They're called the intermedial directions or something.
Right.
Yeah, but now what's interesting in you take out the XY um, axis,
Right, the
X and
vertical and
Y,
horizontal.
and pull them out,
Yeah,
and now you've got a version of the medicine wheel that a lot of people don't see,
that's exactly
um,
right.
because now you've got a big triangle that is north,
Right.
similar one to the west or to the east, and then south and west.
Yeah.
And most people, or a lot of people, draw the medicine wheel in that cross form.
Right.
And but I've also seen it the other way, and now I just realize what it is, that they've created that image right there, and but pull out the 90-degree, um, the original 90 degrees, and you get this other version of north, south, east, west. Then what I think is really interesting is that if you put another intersection in there, um, the bottom will turn into a full circle. And if you could pull the top up, then you got your traditional teepee
Mm.
with a circle base. Very interesting for me, anyway.
Yeah. Except that the traditional teepee, the way I've learned to build them is you start with the tetrahedron, which would bring
Yeah,
these two axes a little closer together. It would be an irregular tetrahedron. The vertical line here would be the back of the tetrahedron. These two would be the
yeah,
front. They'd be a little bit closer together. And then having built that tetrahedron out of poles, then you take 12
Right.
other poles and put them around in a circle, creating the circular
right.
thing. I thought I had a picture of the medicine wheel, and we could certainly go out, I think, to the internet and find that picture because I think people listening to what you said may not be able to visualize that. So let me go out really quickly. I'm going to grab images and then let's share. Yeah, in fact, just all I did was type in medicine wheel into Google and look at all the fun pictures that come up. So here you have your XY, which is
Yeah,
your north, south, east, and west. But over here, this is
there it is.
here,
Yeah,
here are the
Yeah.
medicine wheels we don't often see. And yet they're very common. Lots of good examples of the different variations. And there's your north segment, east segment, south segment, and west segment. And we could go into all the symbology of what that is, but anyway, um, that's pretty cool. Coming back to the book. Any other comments or questions before we head back to the book?
no, I'm really glad you did what you just did, because it really adds a whole new sort of understanding for me in terms of how you get from that 90-degree intersection of a medicine wheel, and how you get to that triangular north, south, east, west version.
Yeah,
Yeah,
very cool.
thank you.
Oh, good. Sometimes, okay, good. We're moving on to page 102, and here we go.
The sought after balance will be achieved by omnisymmetry.
Sorry, go ahead.
That is maximum symmetry. The desired array must consist exclusively of unit length vectors, both explosive and embracing. One way to solve the problem is to picture a square grid of energy events interconnected by vectors. Squares provide an easy starting point because they make up the basic framework of the current mathematics. The XY coordinate system, as before, the length of the vectors which connect events represents the strength of their interaction. Because the distance between the diagonal corners is 1.414 times the distance between the adjacent loci, the attractive forces represented are that much greater. Imbalance or lack of equilibrium in a diagram of forces represents motion. As a result of the attractive forces between neighboring energy events, they push and pull on each other until all the disparate separation distances become equal. Again, like the cookie tray, a pattern of equilateral triangles is established. Every single energy event is a uniform distance apart from each neighbor, and there are 60-degree angles between all vector connections. The forces are finally balanced, and the resulting array informs us about
Sorry for the big jump.
yeah.
Maybe I need to, maybe, hang on. Holy mackerel, it just wants to go. Wow. Unbelievable.
Informs us about the fundamental. Let's see if I have.
Huh. Are we on page 102 or did I just jump a page? I think no, we're on page 102. All right.
Informs us about the fundamental symmetry inherent in a flat surface. Going back to the radial vectoral diagram, we now arrange 6 vectors emanating from a point. The embracing vectors will be the same length as the exploding group. And an inescapable consequence of this fact, obvious in retrospect, is that angles between all vectors are also identical, not just those between radial vectors, but also those between circumferential and radial vectors, figure 3-32.d. No other arrangements has this property because 60-degree angles are integral to equilateral triangles. A
Okay,
diagram.
let's go back and see what there's D right there.
Right.
Oh my gosh. 102. Unbelievable. Well, I have, okay, I don't know. I'm not sure how D works because I've seen better pictures of 60 degrees. I guess I can leave it alone. Okay. Okay, there we go, right? 4D. Now we can make a leap, right?
Yeah. Well, yeah, now a diagram of radial vectors can be thought of as an apple pie divided into some number of pieces. These pieces are always triangular with 2 radial edges and 1 circumferential edge. Because of the fact that the angular sum in every fiat triangle is 180 degrees, the only way for a triangle to have all angles the same is with the 360-degree angles. Therefore, the only angular measurement that will allow us to divide the vector pi omnisymmetrically is 60 degrees, requiring that unity 360 degrees be divided 6 ways. The procedure is straightforward so far. In the plane, equilibrium is demonstrated by a hexagon figure 7-32d. Now we make the leap into space with its accompanying leap in complexity. It may be difficult to visualize a spatial array, especially non-cubical configurations, but taking it step by step, we shall be able to develop and understand Fuller's model. In terms of vectoral dynamics, the outward radial thrust of the vector equilibrium is exactly balanced by the circumferentially restraining chordal forces. hence the figure is an equilibrium of vectors. All the edges of the figure are of equal length, and this length is always the same as the distance of any of its vertexes from the center of the figure. A geometry of vectors, fully reasoned, must be omnidirectional operative, hence radially oriented and omnisymmetrical. Following their planar example, we want some number of vectors emanating from an origin, situated so that the distances between the vector endpoints, vertices, are not only equal to each other, but also exactly equal to the length of the radial vectors.
Okay, let's pause there. So you're reading your own book. I'm wondering where you're reading, and I've had a heck of a time.
Yeah, no, I finally just went through it.
Yeah,
Sorry about
yeah,
that.
that's
I don't know
okay.
if that messes you up, but
No, I'm good. So any comments or questions on this point? Any geometry of vectors, full reason, must be omnidirectionally operative, hence radially oriented and omnisymmetrical. I'm not exactly sure what this whole conversation is. Anybody want to help explain to me what we just read?
I'm learning it myself, to be quite honest. All the edges, I mean, we can see again, here's the idea, all the edges of the figure are of equal length. And this length is always the same as the distance of any of the vertices from the center of the figure. And then that's where we are actually making comments about that when we first started. Um, uh,
Well, that didn't explain much to me.
no, it didn't. Going back. Um,
Um, Richard, do you have anything to contribute to
they're
this?
actually equal to the vectoral radial vectors. No, I don't have a lot to add. I have to digest this a little bit.
Well, I've got a couple. Well, we could just continue. Richard, do you want to read about the cuboctahedron? Or do you want to let somebody else continue to read?
You're on mute, Richard.
No wonder you didn't hear me. I was saying go to that diagram because I think it's an illustration of what was just read earlier.
This diagram here or the diagram on the previous page?
That one, 7.5.
Okay. Oh, I see.
If you go back and read that paragraph that Joe read, I think you should be able to see that diagram.
It doesn't refer to 7.5.
No, it doesn't, but it says it's a geometry of vectors.
Yeah.
And they must be omnidirectionally operative, hence radially oriented and omnisymmetrical. We want some number of vectors emanating from an origin, the center, situated so the distances between vector endpoints, vertices, are not only all equal to each other, but also exactly equal to the length of the radial vectors.
Right on. That does do the vector equilibrium guy right here.
Yeah.
There's your hexagon down here.
Yeah.
It means to be centered.
And so those are all radial vectors that go out of that center.
Oh.
And they're all the equal length.
Cool.
And they're all equal to the boundary.
Yeah,
cool.
to the vertices, out to the points.
So Richard, do you want to read from Cuboctahedron?
Yeah, I can. Cuboctahedron as vector equilibrium. we can understand the symmetry of the plane by observing that although any polygon can be made to have equal edge lengths, only the regular hexagon can have edges equal in length to the distance between the polygon center and its vertices. In the same way, although there are many regular and semi-regular polyhedra with equal edge lengths, there is only one spatial configuration in which the length of each polyhedral edge is equal to that of the radial distance from its center of gravity to any vertex, the cuboctahedron. Wow, that really clarifies a whole bunch of things for me in realizing that, that basically all it's saying is all those lines are equal lengths.
Yeah, the
Right.
big fat thick lines and the little thin lines and the double lines.
And the only way you can do that is if it's hexagonal from the
And
center.
and if you take all these sticks, if we counted them, the shape it would make would be a cuboctahedron.
Yeah.
And it would make no other shape. Well, I seem to understand that. Thank you.
Well, it certainly helped me also understand this idea of the vector equilibrium and the cuboctahedron is basically being the same thing, because especially in some of those trim tab group meetings, there's a number of people who, have a better sort of grasp of all of this than I do. And so very often I've heard people talk about the cuboctahedron and the vector equilibrium, and it didn't really register how they were the same. Now it does.
Yeah, in fact, that is so profound. I'm gonna put it in my directory of definitions because I think that is so really profound. Cool. If you're ready, we can continue.
So talking about this shape, therefore, is the only one that allows the requisite arrangement of vectors to demonstrate equilibrium. Next page.
Right, good. We're going to the next page. I just wanted to. Okay, there we go.
So in 7.6, a cuboctahedron be a twist cuboctahedron. Okay. Oh, I see.
Yeah, what
And
we
the
got.
cuboctahedron is sliced in half, and one hemisphere is rotated 60 degrees with respect to the other. The resulting twist cuboctahedron maintains the radial circumferential equivalence with its asymmetrical arrangement of faces. However, this shape is not similarly suited to model equilibrium. The desired balance of vectors is therefore achieved through the straight cuboctahedron, 7.6a.
Okay, so I understand this. We take this horizontal axis right here and we cut the thing and then twist the bottom by 60 degrees. That triangle moves into here. That square moves into there. And what we have is this guy here. I see it very clearly.
Yeah.
I see
However,
it now that you just described it that way. Yes.
yeah, and the desired balance of vectors is therefore achieved through the straight. If the cuboctahedron is sliced in half and one hemisphere is rotated 60 degrees with respect to the other, the resulting twist cuboctahedron maintains the radial circumferential equivalence. However, this shape is not similarly suited to model the equilibrium. Weird. I never knew that could happen. Okay, good.
It makes you wonder why she bothered to even contrast them.
I think she's just trying to show that
I
if all
think,
the
yeah.
if all the radii if all the radii and all the lines in this polyhedron are equal, you'd either get this shape or this shape. And this shape is not as easy, as fun or easy as this shape. See, this shape seems to have more symmetry. That's what I hear her saying.
And so, I mean, she's by giving us these different perspectives too. I think that actually, she's providing us with that when we look at things from a different angle, how they may appear.
Yeah, but if you take the B model now and then turn the top half,
Right,
it returns it to A.
right. It's kind of like a Rubik's Cube.
Yeah, I'm just
Yeah,
gonna
that's
say
what I was
that.
thinking actually.
Yeah. Yeah, you could split it in any number of directions. If this were a Rubik's Cube, you could bring this guy down and because that should be a triangle up there.
Yeah, if I twist the top, the triangle is just going to slide over, and now it's going to
Right,
be above the bottom square,
right.
which is the same as the the face, the foreground of the one in A. It's a
There's our
triangle
million
over a
dollar
square.
idea, you guys. Let's make this into a like a Rubik's Cube. Manufacture that and sell it, and we'll have ourselves a really great puzzle. We'll make $1 million.
Yeah, because you know the Rubik's cube that you see is a cube,
Right.
but there's also a tetrahedron Rubik's.
And this is it.
Um, no, the tetrahedron is in a tetrahedron shape.
Oh, I
So
see. You've got a
this is
tetrahedral cube. This will be an octahedral cube, which would
and
even be a
so
third shape.
so this is the one that we can really make money off of because nobody else has done
Nobody else has done this.
it.
I'll be the cheerleader.
Yeah.
Okay. Want to continue?
Yeah, so anyway, we first saw the cuboctahedron as the degenerate truncation of both the cube and the octahedron. But at that point in our investigation, we were only looking at surface topology. Now diving into the interior shape, we discover this unique property of equivalence. Table 7.1 compares the radial lengths of various familiar polyhedra given unit edge lengths. Only in the cuboctahedron, hereafter referred to by Fuller's term as the vector equilibrium, or VE, can the radiuses be of equal of unit lengths. So where is it?
Of unit length. What is you looking for?
Oh, we're down at there we are.
We're at the
VE
table.
is the radius is 1, the central angle is 60 degrees, the axial angle is 60 degrees. And all the others are some fraction of 1.
Okay, so what is the central angle in a tetrahedron? What is the central angle in a tetrahedron, and what is the axial angle in a tetrahedron? Somebody please tell me.
Uh,
All right. This leads me, I'm crazy, so I'm going to go over to Google here, and I'm going to ask it. What is the central angle in a tetrahedron? And we're going to have an AI search result here. Oh my gosh, it's not helping at all because it just gives me more mumbo jumbo, but here we go. The central angle in a tetrahedron is approximately 109.5 degrees. It refers to the angle between two lines drawn from the center, the centroid of the tetrahedron.
right.
Where's the picture?
Mm.
I need to see a picture.
Well, if you draw the tetrahedron with the the vertical line sort of pulled out, like
You see a drawing down here that'll help me, Richard?
yeah, I'm whoops, go up one, next row up, and then to the left, to the far left, that one, just below. Well, that one will work too, but go the one below with the dotted lines. The dotted lines are into the center. No, wait a minute, that's not it.
I think this one shows the dotted
No.
lines is actually the form, and that this,
There
well,
it is.
there's
There it is.
109
There it is
right
right
there.
there.
Yeah, this is
So-
109.
And so that's inside.
Right.
And those radii go out to the vertexes. And so it's that angle inside there that's 109.
There you go. That angle that's inside there.
Yeah.
So the red line shows the actual tetrahedron. And whoops.
Yeah.
I and a
That's interesting. All the bond angles around each carbon atom is in the backbone are 190 degrees.
Okay, so I'm going to save this because there we go. So that's the 190-degree angle that we learned about that we just read about.
Yeah. So there it is, 109, right?
Right, that's the central angle. So all three of those angles from the center of that tetrahedron out are all going to be 109.47 degrees.
Right.
And the axial angle must be to the axis. It's going to be 35.26. And the radius, go ahead.
Well, it'd be interesting if we could find another diagram to show the axial angle,
All right.
just so we can see it visually.
We could do that because I'm a crazy person.
Yeah.
And I seem to be not, I don't seem to care much. I just only go for it. So what is the axial angle? Axial.
It's down at the corner, I think, at the vertices.
Oh, look, it's showing me the same pictures.
I did my own.
Do you see axial angle in that picture? It must be the angle up here at the top.
That's what I'm thinking, yeah.
I want to know why when I asked for an axial angle, it basically shows me the same freaking diagram. What is the axial angle in a tetrahedron? Let's make sure that it actually does it. It's doing it. I would sure feel better if I saw something pointed to a thing that said axial angle.
Yeah.
I'm going to get rid of this guy. It's taking up too much of the real estate. Well, I'm so delighted to see this. Or, to be exact, this guy. But I sure would like to see the axial angle. Is that the axial angle down there? M48, visit website. Well,
I'm doing my own little image. Oh, that might be able
we
to.
know that this is the central angle.
Right.
Maybe the axial angle is that angle right there. Because that would be the same in all three triangles, just like this would be the same in all three triangles. But I
Oh,
don't. Isn't that interesting that I asked the question, what is the axial angle in a tetrahedron? And I get the same pictures. This is the dihedral angle, but I don't understand what that means either. Dihedral angle. Again, we're seeing dihedral angle. We're not seeing axial angle.
Yeah, I'm looking at it too.
Well, are we ready to give up? I don't even see anything that says 35.26 degrees. I'd like, show me a diagram that says 35.26. I'll rest my case.
Yeah.
What we could do is we could just do an in-page search for 35.26. Whoops, I put a slash instead of a point. Go for it. There are no 35.26s on this page. Well, anybody have any suggestions or ideas?
There are no 35. What? Hang on.
I certainly keep getting 109 to
109.47.
yeah, or 0.5.
Yeah.
I would have thought this guy would have shown something. Let's go visit this page and see what it says. we're on a journey. I'm going to just do a search on this page for 35.6.26. And there are none. Well, okay.
Try it this way. What is it? 35.2?
0.26, yeah. 35.26. Oh, well. I mean, how can you ask a question more explicitly than what is the axial angle of we'll say of a tetrahedron? See if that makes any difference.
Angle in a tetrahedral molecule, lots of teachers will tell you it's 109.5, but never prove it to you. Here I go. Now, a tetrahedron is the three-dimensional shape made.
Do you want to share that?
Connect two opposite corners.
I'm on another computer, so.
Oh.
So here in yellow, I've drawn a cube for you.
I'll mute myself here.
Well, I'm enjoying listening to it.
Yeah, me too.
And if the guy says axial angle, I'm going to get excited.
In the center, perhaps this is a carbon connected to four hydrogens. And then you connect that same carbon to the other two corners of the bottom face. Note that it's not the same two corners when you're looking down on it. It's the other two corners of the other face. These connect to make you a tetrahedron. Now, all four atoms have to be the same, otherwise there's going to be slight differences in electron repulsion, and it won't be a perfect tetrahedron. But that's not what we're here for. If you're feeling heavy on algebra, you can make these side lengths x, but I'm just going to make them 1 because I'm lazy. Now I want to point something out here. Because I have a square on top, I can use Pythagorean theorem to calculate the length of this diagonal. Now, if I was to redraw this cube,
Can you
from
put that
the
link?
top,
Or
I would
email
have
that link?
connected this corner and this corner. These side lengths are 1, and we are looking to figure out this diagonal distance. Now, to do that, all we need is the Pythagorean theorem. If this is my side length c, c squared equals a squared plus b squared. So my c here is 1 squared plus 1 squared. I told you it'd be easy if I used 1. C squared is 2. And so c itself is the square root of 2. I don't like rounding, but you can round to, like, I don't know, 4 decimal places if you want. Great. So now we have that length there. What I'm going to redraw for you is this cube, looking at it from, like, looking at this corner head on. So what we'd see then is that center mass extending one way to one side of the cube and another way to another side of the cube. Now,
He's
he's
going to end up,
this is the diagonal.
Can you email
he's
that
going to
to
end
us?
up with 109. That's all.
Can you email that to us?
Which one?
Side length, which
No, I'm
takes
talking about
the other
Richard
corner.
emailing
Now,
that
those are
video.
worth 1 each, but because they're actually coming out at you, they don't look that way in this.
Yeah.
Instead, this distance, as we proved here, is just root 2. Great. Now, in order to figure out how long these bonds are, it's going to take a little more finesse. It's going to take the
It's not going to
Pythagorean
work.
theorem
He's just going to
again.
come up with 109.
Take a look at the diagonal that I had drawn for you. It was root 2. This is a cube, so the height of it is 1. If I was looking to connect one corner of one face with the opposite corner of the opposite face, it would take me down the bond and then some. So I can figure out the length of this diagonal also with Pythagorean theorem. In math, it's bad to use the same variable twice, but I'm going to call it C anyways, because I notice high school kids love using angle. Perhaps you already see where I'm going with this. We have something in math called cosine law that lets you solve for an angle. I'm going to call it theta if you know all 3 side lengths of the triangle. Now you could use regular sine, cos, or tan here. You'd have to break the sides that are touching the angle you're solving for. C is the side across from the angle that you were solving for. Same answer. I got root 3 over 2 squared plus another root 3 over 2 squared minus a root 2 squared. All divided by 2 times A, which is root 3 over 2, times B, and there are 2 of them. So I've got to add that to another one of itself. And then I minus root 2 squared off of that. So my numerator here is negative 0.5. I'm just going to do the top and bottom separately. If you don't, angle in a tetrahedral molecule can be found by taking the cos inverse of that number. Now I ran out of clears in degree mode here on my Casio. It's a D. Sometimes it might say deg. If you're in rad mode, you're 109.5. Oh my goodness, the calculator gave it to me. And I'd call that all in one shot, but there were definitely some multiple steps to it. Nice. Can you believe that the calculator is giving you the number that your teacher just straight up says a tetrahedral bond angle is? It's because your teacher didn't make it up. It's true facts. Math proves it. Grade 10 math here in Ontario. I don't know what grade you're in, but congratulations on getting that bond angle with me. And best of luck.
Well, he's obviously from Canada.
Yeah, and he went through all of that and he came up with 109. So he's still not getting at the axial.
Yeah, somehow
So
the central angle seems to be it. But anyway.
Can you
No,
email that video, Richard?
Well, I can do that, but what I did, I just Googled tetrahedron axial angle, and I did 35.2 degrees, and I got that one.
And you still got that one. So
So
it's
I
like
still,
everybody's hiding
what
what.
we're looking for.
That's exactly right. They're going to tell us everything but what we want. And you were even more explicit than I was. Look, if we take 109 and subtract it from 180, which would be the complementary angle here to finish that circle, that's not going to give it to us because 180 minus 109 is 70 something, right? And maybe this right here is that has got to be the radial angle because what we're taking now is we're taking this 190 degrees down here. This is the central angle. This has got to be the radial angle down here.
Yeah, that's what I think too.
I think that is the radial angle.
Because it also is in the ballpark of 45 degrees.
Where is it? I'm sorry.
Right down here,
Yeah,
this
yeah,
little
yeah,
guy.
yeah. That is it.
Bam.
That is it. That's definitely the radial angle.
The radial angle as opposed to the central angle. But how come it doesn't want to say that's what it is? And how come it doesn't want to tell us the 35 degrees? It keeps talking about the 109.5 or the 109.47. I have to log in to get the answer to this question, but I'm sure that is the angular thing. So what I'm going to do is I'm just going to save this picture.
So it's really, what's that? It's sort of D second O, whatever the other figure was.
Okay, in pink. So I've just saved that. And what it's telling me then is that oh, that's the wrong figure. What I want to do is create a new one. And now we want to do this guy here. Whoops, I can't do that because my screen is caca. Okay, new guy. Let's make him a little bit bigger. Okay. Oh, I see. There it is. Okay, here we go.
Yeah.
I wish I knew what the green thing was. Angle and radial angle.
Axial angle.
Oh, axial. Thank you. Axial.
Center and axial.
There you go. Oh, center angle or the central?
Central.
Yeah, it's supposed to be center, and that's the 109.
Have I got it spelled correctly?
Central.
Central. Okay, good. Central angle and axial angle in pink. Bam. Okay, so I'm assuming we're all convinced that big guy there from D to OA, DOA, is the central angle, and we're thinking that probably the radial angle is that little guy.
That looks like it's O base A.
Right. O base A. Yeah, that's what it looks like. Okay, good. Not to be defeated, there's even more.
Yeah.
Octahedron has different size radii. And it's going to have a central angle of 90 degrees, which is kind of obvious to me, and 45 because
Right.
half of the 90. You got icosahedron and the pentadodecahedron. Anybody know what a pentadodecahedron looks like?
Five and 10, isn't it?
Yeah, you're seeing, yeah, penta and dodeca. Well, 5 and 12.
Wow.
Boy, my computer, I just am driving it crazy. Boy, Joe, you got some really cute stuff in there in the chat. Joe's put some really cute stuff in the chat, and the trouble is that stuff will never survive. Let's just have Google.
What do you mean it will never survive?
And it doesn't survive. The chat does not save the pictures.
Oh, really?
Yeah. Okay, here's the pentadodecahedron. Holy crap, holy. Pentacus dodecahedron. That's it right there.
Mhm.
Here's a pentadodecahedron. I don't have any idea because there's,
Well, there's the pentas, there's the pentagons in it.
right.
Oh, wow. Actually, that was it.
Let's go to Wiki and just get the pentadodecahedron right there. Oh, it's not going to show picture. Oh, this is etymology. It's showing the etymology of a pentadodecahedron. Who needs the etymology?
It's got 12
Okay,
pentagonal faces.
there we go. Double pentadodecahedron.
Wow.
Pentacus dodecahedron. Let's see if the Oxford English Dictionary will settle on a picture. Of course not. It wants to sell us 18 things. Okay,
Start, Dave.
I'm ready to get back to biz. Okay, good. You want to finish that, Richard?
Yeah, at the bottom.
Yeah.
Again, in order for all vectors to be exactly the same length, the angles between them, both radial and circumferential, are necessarily equal. In 7.5, the VE is shown with both radial and edge vectors. That has to go back to 7.5. Radial vectors, this
There's
one back here.
7.6. There's 7.5.
There, right.
That's the vector equilibrium.
So they're all equal.
Yeah.
Which is another way of understanding why those two words are put together. Vector equilibrium.
Yeah.
Radial lengths are the same.
Yeah. Radial vectors can connect the 12 vertices to the system's center,
Right.
thereby forming 24 radiating equilateral triangles corresponding to each polyhedral edge and pointing inwardly. We should not be surprised to find an array of equilateral triangles in the VE, for this is the only polygon with equal distances and angles between all points. So that's kind of reiterating the uniqueness of the vector equilibrium cuboctahedron. And as vectors, go ahead.
Well, it's taking me off to an exercise that I got from somewhere in Fuller's work. And the exercise is this. If I gave you like 12 gumdrops, no, 13 gumdrops, and as many toothpicks as you want to stick into those gumdrops, I want you to create a space or a structure that can accommodate 20 sort of independent living spaces for people, the homeless, or something like that. And so right away, you're thinking, I got 13, I can have as many sticks or toothpicks as I want, and I have to create 20 out of 13. How the hell am I going to do that? And the answer is you have the sort of the 12 vertices of the octahedron, and you have the 13th is in the middle, and you connect those 12 triangle faces, and you'll get 20 sort of tetrahedral spaces. And so you could have sort of 20 tetrahedral tents that each person gets their own kind of single unit, living unit.
Right.
Now, I did that at university, when the university has sort of welcome days or exhibit days. And so all the different faculties have exhibition tables. And of course, the engineers and people like that, they've usually got some kind of mechanical system that attracts all the students to that table. And my work in social work, we never had anything like that. It was just sort of like we had some brochures maybe, but nobody comes to want to find out what's in those brochures. So I came up with this exercise, and I said, and I had Ziploc bags of gumdrops and toothpicks, and the instruction, and I also said that the winner, whoever can do this, will get a prize. I didn't say what the prize was. And we had all kinds of students come to that table to try and answer the question. And I gave one of the bags to one of our support staff whose son was about 8 or 9 years old. And she took it home, and he solved it within about 10 minutes.
Wow.
And I still have what he did in my office. And he's now 30 some odd years old. He's an engineer somewhere. His mom, he's a Chinese fellow. And so it was really quite amazing. This young kid figured it out that fast.
Maybe you should bring that to this call and challenge us all to see what we do with it.
Yeah.
Give us an assignment to get gumballs and toothpicks
Hmm.
and see if we can put it together. I'm going to finish this so we can finish this section. We should not be surprised to find an array of equilateral triangles in the VE, for this is the only polygon with equal distances and angles between all points. And as vectors incorporate both magnitude and direction, an equilibrium of vectors must, in Fuller's terminology, balance both angle and frequency. See, I'm not sure what any of that language means. What is balance thing? 60-degree angles are inevitable. So there's some significance on the 60 degrees, Richard, right there. What if we had anticipated the necessity of 60-degree angles? We could have started this part of the investigation by specifying the angle between radial vectors and looking for the resulting implications of that choice. The discovery then would be that the necessary 60-degree gaps in spatial array generate exactly 12 vectors, just as 6 in the outcome in a plane. Had we started thus with the choice of angles, we would have had to check the resulting vector lengths to find out that indeed they were all the same. In either case, the end result is extremely satisfying. Whew. Any comments or questions on that? Okay, let's put this thing together.
Well, if you can see this is what the kid did over 20 years ago.
And you kept it?
Yeah, I've kept it, and I took a picture of it, maybe 2 or 3 years ago, when I had a chance to meet the young boy's mother, because she retired from our faculty.
Oh, wow.
And so she sent a picture of it to her son.
Wow.
I don't know what he thought, but he's probably building bridges in Hong Kong or China or somewhere.
Wow. I'm guessing that gumballs or Twinkies will survive eternity.
Yeah.
So,
Well,
Joe, go ahead.
that was what was happening when the carbon 60 guys were trying to create that curvature.
Uh-huh.
And they had a grad student and his wife or girlfriend, and they were trying to create it through gumballs and toothpicks.
Oh, wow.
And they also were eating the gumballs as they were trying to figure this out. And they run out of gumballs before they
Before they put the thing
Before
together.
they could figure
before
it
they
out.
solve the problem.
Cool enough. So, Joe, how you feeling, and what are your takeaways for tonight?
I'm feeling pretty good, actually. I mean, I did some of my own searching, actually, and I mean, I think that this is an interesting way even to start out with the idea of the way the trays worked in the extra row and how maximizing the use of space. That was an interesting way of actually starting out the chapter, but the main takeaway would be the idea of understanding the center and its relationship as far as to how if you understand the center and you understand the boundary, you can understand the vectors. And you understand the different shapes that are actually in the in whatever structure. So that to me is where if I were to even actually draw an analogy for that, you can make it so that if you understand yourself, if you understand your core of who you are, you can kind of figure out all the shapes that make you up, in a sense that, what's the boundary. And so I think that this is a interesting way of looking at patterns, and I like the way that it was gradually done. So I like the double, was it the double dodecahedron? No, I'm sorry, double
The
penta. Yeah, that
pentadodecahedron.
that was actually really interesting to me, because of the patterns that you can see with and the one that I put in the chat was just very obvious, how it looks like the Star of David, to be quite honest. You could see them, a combination of them all over. So that's what I mean, that was really interesting to me. When you look at that, you could really see that highlighted, and then that started to be able to see the patterns, the other patterns. And honestly, this is kind of the basis for things like the jitterbug eventually. So those are my takeaways. Richard, how you feeling? What'd you take away?
Well, I started out feeling pretty good, and I still feel pretty good. And I really have an advanced understanding now of the way in which the outer edges and vertexes of a basic tetrahedron work, and those 60-degree angles. And now I've worked over time with the idea of putting the inner dot in there and then connecting them out to the 3, or to the 4 actually, vertices. And up until tonight, reading that table 4 wouldn't make much sense to me, and now it does. So I really appreciate that. In a social context, I'm not sure what it means to sort of know those angles. But I do know, much like I think you were saying, Joe, is that if I go inside to that centerpiece and see the connection, then that can represent that inner being. And the way I worked with that concept years ago was that inside part was the notion of one's self-acceptance, one's acceptance of their own just basic integrity as a person. And outside represented for a lot of people the self-esteem, the performance side that they expected of each other or others expected of them. And that the self-esteem was very often the primary driver in one's overall self-worth. And we were trying to work with teenagers who were having difficulties to get them to see that it's got overall self-worth is a combination of self-acceptance, what's inside that soul part, if you want, and what's outside in terms of the performance side, the esteem side, the measurable side, the observational side that people often use to say, oh, you were a good guy, you did, great things, or you failed miserably. And all of that has an impact on your sense of who you are as a person. And so it's finding with the tetrahedron, then, for me, it's the idea of what's inside that framework that we were talking about and the overall outside part. The combination of those two ends up with the holistic, if you want, notion of self-worth. And it's made up of a minimum two, in this case for me, the self-acceptance and the self-esteem. And so when we're working with young people, we wanted to build up their self-acceptance so they could go out and try something and fail and not be devastated by it. Or we wanted to give them a sense of success in doing something so that they could go over and feed their self-acceptance and sort of say that, see, I am okay. But because some of the kids were really seriously troubled, we didn't know which road to take. And we ended up saying, to hell with it, we're going to have to, we called it double bag them. We're going to have to try and do something that'll boast their self-acceptance and boast their self-esteem all at the same time in order to elevate their overall self-worth. And became very clear that that wasn't an easy task when you're working with human sort of social relationship issues and the pressures that, and I didn't know anything about tensegrity back then, but to know the pressure on you to behave according to society and the tension that's between you and the systems around you that are either supporting you or making the tensional stress even worse, compounding it. So this is very helpful for me tonight to have a better understanding of those physical kinds of geometric figures and how they may or may not apply in a practical social sense. So over to you, Steve, and
Yeah.
how you're feeling. What are you taking away?
Well, I'm excited when what you just said, because one of the things that I've been pondering as we talked tensegrity is the etymology or the vibrational etymology, what I like to call vibrational etymology of the very concept of intention. I have a tension, I have compression, I have all these things going on, but what's my intention? And can I create an equilibrium that allows me to grow through whatever compression and things I'm going through? So that's adding a little bit to my intentional thing. This whole idea of the cuboctahedron, the cuboctahedron and the twisted cuboctahedron, I'm totally convinced that's the next $1 million toy. And you can take that thing on any of its great circles and just twist it in any direction, and it'll go from a cuboctahedron and you twist it one notch and it goes to a twisted cuboctahedron. You can take any of those radii, those great circles, and you can have some major fun with this thing. So if I knew how to build a Rubik's cube, I would do that, but I don't. So I'm going to give up and let somebody else make the $1 million. Um, um, I really am excited about the epiphany about the cuboctahedron. I've always wondered why this is the vector equilibrium, why Bucky starts here with the jitterbug. How can the cuboctahedron be the basis of all of the um, geometry that I see around me in every way? And understanding that all the radii are exactly the same and all the angles are exactly the same. And if I take that 60-degree angle and I take those radii and I make them all the same, no matter how big they are, if they're all the same, I'm going to freaking end up with a cuboctahedron no matter freaking what. That was a blow away for me. I'm very excited. It's like, okay, I see the cuboctahedron. I could tell you intellectually what it was, but now I really get why it's so freaking significant. And I'm going to have to ponder on that and make sure that I'd have that totally integrated. But I'm very thrilled about it. This was really a good discussion night. Thank you all. We've gone a little bit long. We started a little bit late, but thank you all for allowing me to finish off that last page and get us to the next heading. Where we will begin next week on page 105. We're going to talk about VE results, whatever that means. You guys are my favorite Saturday night activity. I don't know if that's good or bad.
Yeah, I was about to say, yeah. Richard actually,
That's pretty good when it
Could you
beats a
send that
rock and roll
video?
band.
can you
Yeah.
send Richard, can you send that video actually, if you mind? It didn't come up for me.
Oh, okay. I'll go see if I can find. Yeah, okay.
Yeah, the
Cool.
one you were just playing. I
All right.
appreciate that.
Okay, my favorite guys. And we'll see you all next week.
Yeah.
Bye-bye.
Take
Bye now.
care.